So now let us see the Carnot cycle. So Carnot wanted to increase the efficiency of his heat engines, and he didn't work out on the mechanical details, instead worked on the basic principles. So we are not going into the details of the Carnot's engine, but the basic theory of its Carnot cycle, the basic thermodynamic process we are talking about. So let us see what's a Carnot cycle. So a Carnot cycle, in Carnot cycle we talk about a cyclic process. So in Carnot's cycle, we talk about a cyclic process which can be carried by any type of system. It can be any type of system. It can be a surface film, a paramagnetic salt, an ideal gas system, or anything. So, but here we will concentrate with only one case in which we take an ideal gas system. So we consider here an ideal gas system which goes through a Carnot cycle. So now let us see how the Carnot cycle will be. So in a Carnot cycle, what we do, we will represent our process in a Carnot cycle on a PV diagram. So in Carnot cycle, here we will have two isotherms. So this is one isotherm, this is T2, and there is one more isotherm, there will be T1. So T1 and T2 are two isotherms. So we will consider our process from A, and first this process is carried to a state B, and then it is adiabatically brought to a state C. So let us B be here only, and we have brought it to by an adiabatic process to C, then again here, and you see this is what we are going to talk in the Carnot cycle. So let us concentrate on this graph. So now the Carnot cycle contains two isotherms. These are two isotherms, A to B and C to D, and two adiabats. So adiabatic curves are more steeper than isotherms. So these are two adiabats. So first you see, the system is isothermally expanded from A to B, during which the temperature was T1 and volume increased from VA to VB. So here you can see the volume is VA and here it is VB. Here it is VC and here it is VD. So this is the first, that is isothermal expansion. Next, the gas is adiabatically expanded so that its temperature falls from T1 to T2, and thus during adiabatic expansion the volume expands to VC. So we have one isotherm, one adiabat. Next, from C, the gas is isothermally compressed to D such that from D it can be adiabatically compressed back to A. So D is selected in such a way that from D it can go back to A by adiabatic compression. Again, so thus the cycle is formed. So this cycle is Carnot cycle. So now let us see what is the efficiency of this cycle. Now let us see the process AB. So consider the process A to B. We use delta Q is equal to delta U plus delta W. This is the first law. This process is isothermal A to B. So let us assume that in this process, since temperature is not changing and the volume is increasing, that means system is doing work. This is only possible if the heat coming from outside is Q1. So from outside Q1 heat comes. So let us assume this Q1 heat comes from outside. Delta U is 0 and work done is number of moles nRT 1 ln VB by VA. This is the work done by the gas. The gas is performing work. This is equal to nRT L1 ln VB by VA. So this is 0. So write this as this. So we have Q1 is equal to nRT1 ln VB by VA. This I will write as my equation 1. Now come to B to C process. So consider the process B to C. So now come to process B to C. The process is adiabatic, so no heat exchange is taking place. So we will use T V to the power gamma is constant. So we have T1 V B to the power gamma minus 1, sorry, it's gamma minus 1 is equal to T2 V C to the power gamma minus 1 is equal to constant. So we have this as equation number 2. Now let us come back from B to C, then now C to D. So consider the process C to D. This is again an isothermal process. So in this process, the volume is decreasing, the temperature is constant, means heat is rejected. So heat is rejected, suppose I say it is Q2. So rejected heat is, suppose I say Q2. So that will be actually minus Q2 because it is rejected, and no change in internal energy by nRT 2 ln VB, final is VD by VA. So you see this VA is more than VD. So anyway, this is Q2. So we can further write as Q2 as nRT2 ln VA by VD. This is VA I have brought, so minus will cancel and it will be easy. This is equation 3. So no minus, so it look nice. Now the final process D2A. So consider the process D2A. Again, this is an adiabatic process, no heat exchange. So we will write T V to the power gamma minus 1 constant. So here T2, this is T2, Vd to the power gamma minus 1 is T1, Va to the power gamma minus 1. This is equation number 4. So now let us use these two relations, 2 and 4. So from 2 and 4 we get, suppose this is T1 by T2. So here T1 by T2 gives Vc by Vb to the power gamma minus 1, and from here T1 by T2 I will get Vd by Va as to the power gamma minus 1. We got Vc by Vb is equal to Vd by Va. So this is the relation we got from the two adiabatic processes. Now let us find the ratio of Q1 by Q2. Now Q1 by Q2, this by this, let us see, it is nRT1 ln Vb by Va upon nRT2, this is nRT2 ln Va by Vd. So now you see, here small Q2 is equal to nRT2, this is from C to D, Vc to Vd. So this is actually nRT Vc, this is A is C actually, A is C. So Vc, let us replace this Q2 as Vc by Vd is equal to Vb by A. So actually from here these two terms are equal. Vc by Vd is equal to Vb by Va. So these two terms are equal and so they cancel out. These two terms cancel out. So what we got is Q1 by Q2 is equal to T1 by T2. So we got Q1 by Q2 is equal to T1 by T2. Now let us see what is the efficiency of this Carnot engine. So efficiency of a Carnot engine is given by eta is equal to work by heat input. So this is the general. So work by heat input. So you see work will be Q1 input minus Q2, the heat rejected gets converted into work, by Q input. So we have efficiency as 1 minus Q2 by Q1, that is equal to Q1, that is equal to 1 minus Q2 by Q1 is equal to T2 by T1. So the efficiency of a Carnot engine is equal to 1 minus T2 by T1. And very, very important point here is the Carnot engine is a reversible engine. This is very important point, reversible engine. So all the processes here are reversible, and so the Carnot engine, which operates between two temperatures, the source and the sink, the source at T1 and this T2, the efficiency depends on the source temperature and the sink temperature. This is the expression for the efficiency of a Carnot engine.